Hey everybody, it's the founder of KartFab here. Today I'm taking this old Honda GX390 and I'm turning it into a stroker. So let's go check it out. What's up guys, this is Grant and we're coming at you with another small engine build video that goes over the steps to build a bored and stroked Honda GX390 engine. We're going from 389 cc's, about 11 to 13 horsepower, all the way up to 440 cc's and about 30 plus horsepower. Here's a quick summary of what we're going to see throughout the entire build. We're going to look at engine disassembly, boring to 90 millimeters, block preparation, starter installation, connecting rod installation with plastic gauge, checking for oil clearances, clearancing the block to rod, clearancing the camshaft to the connecting rod, installing oil seals, cylinder head work, which includes porting, polishing, valve lapping, checking the cylinder head volume or CCing the head, piston milling, checking the piston ring end gap, as well as clocking the rings depending on which type of piston you have, camshaft installation, valve geometry, we're talking valve train, which is valves, roller rockers, and push rods, and what to do when your valve geometry is off by using cut to length push rods and spacing up your roller rockers. Towards the end, as the build progresses, we'll be looking at engine timing, how to find top dead center with your cylinder head off with a dial gauge, as well as with your cylinder head on with the piston stop, so you can set the proper timing for your engine build. And finally, we'll be looking at the way your engine breathes through the intake, getting a high flow intake adapter, ditching the old carburetor, getting a flat slide mikuni carburetor, port matching, then putting on a high flow exhaust header, slapping it on a mini bike that will now have 5 times the amount of horsepower as the stock mini bike had, and then going around riding it, doing burnouts, sending it, so on and so forth. So let's go check it out. As you can see here, the cylinder bore is completely shot. Fast forward 2 weeks after sending it to a machine shop, the difference is night and day. I took a forged piston to my machine shop and they bored out from 88 to 90 millimeters, so we're back in business. Speaking of business, this governor has no business in an engine. I'm just taking it out, drilling and tapping the holes, and putting a bolt inside there to keep everything secure. Moving on to some goodies, we're putting a 70 millimeter stroker crank in there instead of the stock 64 millimeter crank. And this has a timing gear that goes on the crank, and we're heating it up with a heat gun. So as you know, something that's cold will shrink and something that is hot will expand. And it makes it really easy to install the timing gear on the crank if it's really hot and it's really cold, so it'll just slide right on. Normally you have to press it on, I don't have a press. It's just a little po' boy innovation here. Works like a charm. Next up is replacing the crankcase side cover bearing with a brand new bearing, replacing the oil seal as well, and then putting a bearing on the flywheel side. I got a starter online, link in the description, and my engine block actually didn't have a starter or a spot to put the starter. The casting, however, does have spots to be tapped, so you can go ahead and install a starter on a block that never had a starter to begin with. Just like so. You just use some bolts and you bolt it right in there after drilling out the hole, which will allow you to use an electric start ring gear for your billet flywheel. I drilled and tapped the low oil sensor. This is me removing the countershaft bearing the wrong way. Yeah, so there's that. On to TIG welding. This is my first time actually using my TIG welder to weld aluminum, so I'm not sure how it should look, but you know what? I welded the little pieces together, put them on the block, welded all that together, and it doesn't leak, so let me know what you think. The next step is setting your bearings and checking your oil clearances in your connecting rod. So you basically take your connecting rod apart. Notice it has no bearings in it. These are the bearings, and they have a little notch on it, as you can see, and that notch fits right inside and kind of holds everything in place. Same thing for the end cap. You have a little notch there. You kind of just push it into place with your fingertips. And this is plastic gauge 0.002 to 0.006. That's 2 to 6 thousandths. And you open your package, cut your plastic gauge into little pieces with a razor blade, and then you just want to go ahead and set it down within the inside of your bearing right here. Once you have your plastic gauge positioned right where you want it, take your crankshaft, make sure that it is free of oil, so wipe down and clean, and then put on your end cap. This is a 12-point socket that you use to install the ARP bolts that come with the connecting rod. You put it on your torque wrench, torque it down. You're torquing this to get everything torqued down to spec, which in this case is 26 foot-pounds. So after you get it all torqued down, get your plastic gauge on it, do the final torque down, that's when you get your final clearance. Looking at your squish of your plastic gauge, you compare that to the wrapper. 2 thousandths, nope. 3 thousandths looks just about right. 4 thousandths, no way. So if you're curious where I got this from, I have a link in the description for that, so you can go check it out if you want to check your own oil clearance. Speaking of clearances, these are feeler gauges. They are what you use to check a variety of clearances within your engine. Within this specific case, we are looking at our ring end gap. That's your piston rings, and checking the gap between the two. Take your ring, install it, then take your piston, flip it upside down, and push it into the bore so everything lines up perfectly. This gets your ring just where you need it, so you can check the ring end gap. Take your feeler gauge, put it in between the ring end gap until you feel a very slight drag, and that's how you check your ring end gap. In this instance, my ring end gap was 9 thousandths. I was able to get such a tight clearance because I had my block bored and honed with a torque plate. Now we are installing our piston and our connecting rod together. You basically want to use a magic marker end. That's kind of what I use, and some pliers to push everything into place so it doesn't really scratch up your piston. But you put your wrist pin in, your connecting rod, put it all together, make sure there's wrist pin circlips on both ends, and go ahead and install your crank. If you're paying attention, you're going to notice I put my piston in without the rings, because I'm not actually assembling my engine yet. I'm checking clearances. Clearances are extremely important with any performance build, because if you don't clearance your engine, you're going to have things hitting in all sorts of places. Since this is a stroker, I have 94 thousandths of an inch pop up, so I got to get a different connecting rod, and I have to shave some material off of my piston, as well as this little windage tray right here. And this is what it looks like after I clearanced it and cleaned it out. While I wait for my other parts to arrive, I'm getting a few additional things taken care of. The first of which is cleaning out my block to get it super clean. The next is installing the flywheel side oil seal. The other seal that I had came with grease, this one didn't. I don't know why, but here we are. Moving on to the cylinder head, a lot of the stock parts need to go, like retainers, springs, valves, rocker arms, that type of thing. So we're just getting rid of all of that. On the right are the stock springs, stock retainers, stock valves. On the left is stainless steel valves, aluminum retainers, and heavy-duty valve springs. Notice the valves are longer. More to that later. So I'm not going to do any head milling because it's a stroker and I wanted a 10.2 to 1 compression ratio. So I'm just going to go ahead and do a light valve job, lapping them. Going to look at the marks. Left is the intake, right is the exhaust. That's exactly where they need to be. The next step is to obtain your cylinder head volume. So what we're going to do is what is called CCing your cylinder head. Basically, put a little grease on your valves and take some plexiglass, grease, isopropyl alcohol, and a very accurate burette. I got a link in the description for all that if you're curious. But you basically coat a little bit of grease on there so it doesn't leak out. Put your plexiglass in there. Fill up your burette until the meniscus, that's that little part of the bubble that's on the bottom, read 0. Add your stuff. You want to add very accurately, not spilling any, and then do your final reading. So once you get your final reading, you know what your cylinder head volume is, so you can calculate your compression ratio. I got a link in the description for that. So now it's time to do a little more work with our piston. Alright, so I'm on my way over to Dennis's house. He's got a mill, and we're going to go ahead and mill that piston down the 45 thousandths that it needs to be milled down to have it 5 thousandths in the hole. So let's go check it out. Hey everybody, I'm over in Dennis's garage. He's going to be milling my piston, and I'm going to check out some of his go-karts while he's doing it.
We're going to try and do lathe work on a milling machine. I could dial it up and know how much I'm taking off, but this tells me, you know, what I started with before I figure out what I ended with.
Cool. We're using a little bit of manila folder to keep from marring the edges of the piston when we get it torqued down. It's pretty close.
Yeah. Ready for this?
I hope so.
3 thousandths away. .681.
Okay. 44 thousandths. Then a little light sanding on the top, and that should be dead on. Awesome. So you're gonna clean up all these chips, right?
Yeah.
This is the piston after we sanded the top down just a little bit. That keeps the fuel atomized as it's coming into the cylinder. And we're going to go ahead and put it in the bore for the final time. So we take the piston and we need to put the rings on it. Again, we take the top ring, mark up, second compression ring, mark up, and oiler rings. Now that we have the rings on the piston, we're going to take the wrist pin and put it inside the piston. We're going to take the snap ring, that holds the wrist pin in place and put it on both sides. So we'll basically put a snap ring in one end, put the wrist pin in the other end, and then put the connecting rod in. So now that you have your rotating assembly almost complete, just think of the way that it should be rotating in the engine with the crank in it, and that's the way that the rod should be oriented. So we're going to pull off the rod end cap and go ahead and install it on the crank. This is the crankshaft. I had it balanced to the connecting rod and piston. It just helps with vibrations. A lot of times with these bigger engines they have a counterbalance in there, and I took it out because we want to rev high. Okay, so that's pretty much it. That's how you put it in. This is going to be first compression ring, second compression ring, top oil, ring expander, bottom oil. Okay, so I'm not going to go into why I oriented my piston ring end gaps this way. Just keep in mind that if you have a certain performance piston, this one happens to be a forged piston, you might need to orient them at 180 degrees or 120 degrees. You might only have one compression ring. So look at your user's manual or instruction manual for your specific piston so you can orient your rings correctly. If you don't have instructions, usually the best way to do it is not in line with the wrist pin like you see here, but 120 degrees apart. So just take that as a grain of salt, keeping in mind that you need to look at your own instruction manual to get it right. So what you see here is a piston ring compressor. I've got a link in the description for that. You want to have the bottom of the skirt of the piston poking out a tiny bit, torque it down, and you'll actually see right here I'm using a heat gun to heat up my block just to give me a little bit of expanded metal there so I can get it all to fit in, because it's a real huge pain in the butt. So once you have the rod in there, torque the rod end cap to spec, which is in the instruction manual for your billet connecting rod. Okay, so I've got the Honda GX390 stock lifters, okay? They just go right in these holes. I got the engine cranked off to one side just so they won't slide out. That's the spot where the cam goes. So you put a little assembly oil right in this journal here, and you can go ahead and install the cam. So moving on to the camshaft, if you can see that little dot on the crank, that dot is the timing mark for the crank gear, and it has a corresponding dot on the camshaft. So you just sync them up and you've got your timing set. Some of you may be wondering, why did you cut up your side cover? What is the purpose of this? This is extremely important, and it's a very valuable tool in any engine builder's toolbox. This is an old side cover for this exact same engine. I think this is actually a knockoff $20 version. Anyway, what it does is it holds the crank in place, because if you don't have this here, the crank will actually slide down a little bit. You'll have the camshaft maybe not in the exact same position or not meshed correctly with the crank gear. And what you use this for is to hold the crank in place, hold the cam in place while you check your engine clearances. That's why the side cover is cut. Okay, so you take your feeler gauges, your eyeballs, you check the camshaft lifters, make sure the lifters aren't contacting the block when the lifters are lifted higher with the performance cam. Make sure the cam lobes don't hit the crank or the connecting rod. That's extremely important, because if you don't have this here, they'll sit in a different spot if you just look in the side cover. So when you have this here, you know when you're checking clearances, they're right where they need to be. This is exactly what I'm talking about. The camshaft, crank, and connecting rod are very, very close. Now this is with what we consider a quote-unquote mild camshaft, so it's extremely important to check these clearances. Getting the engine a little bit more, this is what we've got. Contact between the rod and the camshaft. Not the camshaft lobes, but the actual shaft between the lobes. So we are going to have to be able to clear that. When we say clear it or check clearances, we mean check it. If it's touching, grind it away. This is the final product after clearancing. We're looking at the camshaft in between the lobes. That was the only spot that was removed. It was actually only the casting flaws that were ground down. Not a lot of material was removed. You want to make sure that your clearance is anywhere from like 20 to 50 thousandths of an inch between rotating parts. The reason being is the crank actually flexes a little bit, so you want to have a little bit of extra space in there so nothing touches at high RPMs. And there it is inside the block. Notice the daylight between the camshaft and the rod that wasn't there before. Alright, so what I've got going on here is this is the connecting rod. That little arrow is the exact spot where the lobe of the camshaft hits. So I've basically put it in a 1 gallon Ziploc bag because I do not want to take out the piston again. Or I never want to take it out ever again, okay? Such a pain in the butt, okay? So I'm just gonna go ahead and Dremel it out right here in this bag, pull the bag off, spray out the inside of the engine compartment with a carb cleaner, then oil it all up and put it all back together. Okay, there it is after it's all cleaned off. That spot right there. Just a little bit shaved off of the connecting rod, a little bit shaved off of the camshaft. It's a very tight fit, but it does clear. Notice the camshaft lobe now clears the connecting rod, and it's just on one little tiny portion of the rotation. So now it's time to close this short block up. Everything's timed correctly, clearanced, putting on an OEM gasket for the side cover, and torquing the side cover bolts to, I think, 16 foot-pounds. This is some gasket maker for the valve cover spacer. I'm putting a spacer on, then putting the valve cover on top, torquing it down, letting it set up. And you'll see here in a second why I need to put a valve cover spacer on. These are roller rockers, okay? And the valves that I have are aftermarket stainless steel valves. And these valves are about 7.2 millimeters longer than the stock valves. Having ratio rockers and longer valves is going to create an imbalance in the rocker arm geometry. So we actually have to bring those ratio rockers up. So looking here with a little flashlight, there's a mark on the end of the valve tip. If you can see that little line right there in the shadow, at the tip of that shadow. What that is the indentation from the roller. And the indentation is just on a little bit of dry erase marker. And that shows where the roller spans from top to bottom. And it's a little bit higher on the tip. We want to have it on the center of the tip. So we actually have to raise the rocker up a little more to correct the valve geometry. So what that means is basically space up the roller rocker itself and increase the length of the push rods. And we do that by having an adjustable length push rod to get the length in just right, and then cutting our push rods and assembling them. After having adjusted the push rod length as well as spacing out the roller rockers, I've turned the engine over with dry erase marker on the tip of the valve. Notice that mark up top is there, and down on the bottom is right there. So where the roller tip rolls on the tip of the valve is roughly centered. So this will give us maximum lift for our given setup, as well as keeping the valve train stable. Moving on to the next area of valve train, we're looking at spring install height. That's the height of the spring from the bottom of the retainer to the actual head. And it should be around 1.2 inches for what I'm doing. So I'm actually going to need to cut out this washer, cut out the center of it, and space it out. It should be about 1.2 inches, and we're at 1.265 for the intake. So we need to space that intake tighter. It's actually too long. So the thickness of this little washer here is about 60 thousandths of an inch. So that should get us around 1.2 inches install height on the intake side. So moving on to the exhaust side, I went ahead and measured that with my calipers here, and we're at 1.188. I don't have a super high lift cam. Ratio rockers I checked for spring bind, and we're not getting any coil bind there. So we just have to focus on the intake, not so much the exhaust. Going back to push rods, I use this chop saw to cut these cut-to-length push rods. These are chromoly push rods. They don't flex, and they can withstand that higher spring pressure. And I cut them to within 1/1000th of one another. So it's very precise to use that chop saw. You just grind a very tiny bit off the end, and you actually have to press them together. So if you don't have a press, you can just use a hammer, but you don't want to hammer the ends. You take your old lifters, because when you do an engine rebuild, you should replace your lifters with new ones. because when you break in your camshaft you need new lifters anyway. So you just place the ends together and you just hammer it just like so, and it will not mark up the ends of your push rods because those lifters are cupped and it spreads out the force. So that is the end I just pressed in. It's actually pretty sweet. It's just a little tip there for building an engine with cut to length push rods. Moving back to those roller rockers, the studs that mount the roller rockers to the head were too short. So in a little po' boy innovation, went down to the hardware store, bought the same grade bolts, and actually checked it up to a drill and bench grinder to grind them down to the right size. So there they are, with a little bit of red Loctite to hold everything together with the spacers intact. And a quick valve lash set, and we are done with valve train geometry. Of course, got to polish up that valve cover. Moving on to porting and polishing. This is something I've already covered in previous videos, but just to kind of do a quick recap, this is what it looks like before it's ported and polished. This is kind of halfway through where we are taking the sharp edges off the port to bowl transition to increase flow. We do that with a Dremel and some Dremel attachments. I've got a link to all of those in the description. And then we are also matching the seat to the bowl. Now if you look here, you can see my fingernail catch right there, and that is just a transition we want to get rid of and actually open up the seat a tiny little bit, and then after some sandpapering you can kind of see what the final product is. Now this isn't anything super heavy duty. It will only increase your flow if you knock down that port to bowl transition. There are basically two ways to check top dead center accurately. This way we already kind of went over. It's with the dial gauge with the head off, and then you mark where your top dead center is with a little wire you attach to your block, okay? Second method is with this piston stop. I've got a link in the description for that, but you basically rotate your engine almost to top dead center, install your piston stop, and then rotate it until the piston touches that piston stop. And that will give you a measurement on your degree wheel, okay? Once you get that measurement, you turn the degree wheel, or you rotate the engine actually over in the opposite direction, and then it'll give you another measurement. So just to kind of give you an example, right now we're at top dead center, okay? So when we rotate it over, it should hit at the same degree, which is 24.5 on both sides if top dead center was truly top dead center. So we rotate it over here, it should hit at 24.5 on the other side. Okay, perfect. How do you get top dead center without removing your head and without a dial gauge? All you need is your degree wheel, wire, and piston stop, and then it'll give you two numbers. How you get those numbers is you install everything about top dead center, rotate it over, get that number, rotate it over, get that number. So those two numbers where it hits on one side and the other are going to be different. So hypothetically speaking, let's say you hit on 30 on one end and 20 on the other end, okay? All you do is add those together, divide by 2, and that's where your wire should sit. So 30 plus 20 divided by 2 is 25. So you move that little wire over, and it should hit on 25 when you hit the piston stop rotating one direction and then rotating in the opposite. And then when you remove your piston stop, top dead center will be top dead center. What we are looking at here is the adjustable hub for my billet flywheel. Some of the flywheels don't have an adjustable hub on them, but mine does. I went ahead and lapped it lightly to the crank to get it all seated in there, and I set my timing using a timing light, and already knowing what top dead center was, I set my timing to fire at 28 degrees before top dead center, also using these marks which have to do with using my timing light. So I'm not going to go into the details there, but I am going to show you my device that I fabricated to lock the crankshaft in place while I torqued my flywheel down to spec using a torque wrench. Switching gears to the intake adapter, which is pictured here, we need that to install a very large carburetor which will let our engine breathe, which is what we need. So I did a little bit of grinding on the intake adapter, and I also needed to remove a few things. One of which is this stud here. There are actually two studs that held on the stock carburetor, which is very restrictive. and I put on these two nuts on the stud and removed it. They basically tighten against each other, and friction holds them from rotating against each other so you can get that stud out. After installing a gasket and putting the intake on, I used these Allen head bolts and I kind of cut them to length so everything would fit in the way it fit before with the original studs. Now this thing right here is a nipple, and it's used to power a fuel pump for a different type of carburetor. Mine is gravity fed, so I'm just going to take that thing out and plug it. Now that we have the easy part of the build finished, let's put this engine on a bike. This is a Baja Warrior, and it originally has a 6.5 horsepower engine like this. We're going to go ahead and make it fit. I don't care how we're going to do it, we're going to make it fit. I have the engine raised up, and it's touching the frame there. It's touching the frame there, sort of, kind of close, right? So, oh man, it's going to be tight no matter what. So as you can see here, I actually raised the engine up with this engine mounting plate, and I rounded off part of the block. This is the jack shaft. We have tubing that's fish-mouthed, tack welded it into place so we can adjust for the torque converter and the jack shaft sprocket. We want to get the torque converter lined up just right so we can have everything line up perfectly. Same thing for the output sprocket for the jack shaft that goes to the rear axle for the mini bike. So I'm using a straight edge here on the rear axle sprocket, and we're making sure that sprocket edges line up to one another. This is the process of fish mouthing a tube, or more technically called notching with a tubing notcher. Basically, it's just a hole saw that goes on the end of a shaft that cuts through the tubing. So we need additional supports for sure. This is literally a cheap Chinese mini bike that brakes with a 6.5 horsepower engine. We're putting upwards of 30 plus horsepower on it and adding about 100 more pounds. So we need all the support we can get. Now that we have the bulk of the fabrication done, there's just a few minor details. This is the exhaust header with a lip on it. We're going to just knock that lip down with a die grinder. Not a huge deal, but it's just a small detail that you could miss. Now that I have the header on, I noticed it's blowing onto the frame. That's okay. Torque converter, it was oriented differently, so I do have to clean it and put a red spring on it, and now we're going to send it. Set to run. We're gonna choke it, partial throttle. All right, let's go drag race. There they are. Here we go. thanks guys for watching this video. If you like it, give it that thumbs up. It helps me out a ton. It took a lot of time and effort to get this video edited and out the door. Also, if you're seeing this for the first time as a non-subscriber, consider subscribing because we got a lot more coming down the pipeline. We got dyno testing, we've got a Manco Thunderbird mini bike build, we've got a Fox Conquest, go-kart restoration that I'm working on right now, and we got a lot of other cool stuff coming down the line. So thanks guys for watching, and we'll see you in the next one. Peace.